Well, thank you all very much for this opportunity to talk. Really excited to have this following the Middle Conference. I mean, it's a perfect pairing between the advanced research that's going on and then the software that supports it. And MONAI is a continuation in my career of a strong passion for open source and open science. And so I want to share some of that passion with you today and some of the motivation really that went into the creation of MONAI that I've been helping out with. And I want to make it relevant to you, show that this open science idea is relevant to you, whether you're in academia or in industry. Anyway, without further ado, moving on to this. What is open science? I'm going to give a couple of stories or motivations behind it. Maybe you all have seen this. We're kind of living in a Dilbert world or whatever this cartoon is. And so situation, is common. There's 14 standards that you have to choose from. So one of the common things that you do, especially as a grad student or as a young professor, and think, oh man, this is horrible. There's 14 standards. Let's go ahead and come up with one thing that tells all of those different standards, brings them all together. It's going to be the great unifier of them all. Well, next thing you know, there's 15 standards to build from, right? And so this just continues to propagate. And then also, in a more serious bend, you have a situation where this is a study that was done or published in Nature back in 2012, so quite some time ago, but still very relevant. And these two heads of research labs in academia and industry got together, and they were in the field of radiation oncology. And they wanted to go ahead and look at the seminal papers that were out there, the papers which were really driving clinical practice. And so this is how patients with cancer were being treated, were based on these publications. And they wanted to replicate that work so that they could then extend that work, all right? Use that, establish as foundation and build upon it. And what they found out was that 47 of the 53 papers could not be replicated. They were not able to replicate the results that were driving clinical care. All right, nothing malicious was going on within these papers. But if you've all tried to duplicate a paper before and implement the algorithm that was described in the paper, you realize there's hidden parameters, there's all this other stuff going on that it's hard to convey using just a journal article as a publication. And so this is a real challenge that we have nowadays that exists back in 2012 and exists today and actually even existed further back. So if you look at Descartes, he realized that when he did his discourse on science, on the scientific method back in 1637, he said that really science has to be reproducible. That is a basic tenet of science. He said, doubt everything that isn't evidently true, anything that cannot be reproduced. All right, so this is just really a foundation, whether it's in a joke, whether it's in replicating results or in this original publication back in 1637. And really to address all of this, it's the unifying theme of open science. And I heard the term open science from Terry Yu at National Library of Medicine back in about 2000, 2001. And I've just been fascinated with it ever since. And what is open science? Well, it is reproducible science is what it comes down to. It's science where you're, relevant to us computer scientists and MONAI and so forth. It's the code, the source code is released and made freely accessible to everyone. Sharing the data then that you processed using that code in order to then write your publication, which you then also make freely available. So by sharing the code, sharing the data, sharing this publication all together, your science is reproducible. Your science is real. It's evidently true. And this is really the motivation behind MONAI. And you can think, man, this is great. I'm happy to use this. But, sharing my data, sharing my publication, this seems like a hassle. I mean, it's a lot of additional work. People always talk about IRB approval and all these different hurdles. Well, more and more, these are being overcome. And, what I found in my lab, I used to be in academia before I joined Kitware. I found in my lab that by adhering to the principles of open science, even within my research lab in academia, just within my small team, getting them all to practice this, even though it took effort to get them to put their data in a common location, to document their code, make it so that other people could run it, all those basic things. The payoff was just huge for my research lab. And so what I found was it's a great avenue to getting funding. All right. If looking at VTK, the visualization toolkit, that's one out there. I've submitted some grants on that. I've had 2 consecutive R01s on that, and they total about $7 million. Any academic would love to have that as their basis for continuing their research lab. And then if you look at in terms of citations, we have 2 publications that were done when VTK was originally released. And these publications now have 13,000 citations for them. If you use VTK, we ask you to cite one of these 2 papers. 13,000, that's a huge, bonus for anyone's H factor, their impact factor that they have. Great pathway to tenure as well. And then also there's just impact in general, looking at how many times the software is being downloaded as one metric. We're now at 1 million downloads just for MONAI alone. And if you combine MONAI, CMake, VTK, ParaView, 3D Slicer, and these others all together, we see 1 million downloads occurring per month within them. And so this is just massive impact. And that's a lot of motivation for people getting into academia and industry. And then lastly, if you do go into industry, we find that by basing your products, by basing the work that you do on open source code, you're going to reduce your business risk and you're going to reduce your startup costs. You're standing on the shoulders of giants. You've got these, $7 million just for VTK. ITK's original development was $13.5 million. That's a small business not having to invest $13.5 million to come up with a software foundation, but they can build upon it. And so I recommend this for all of y'all. And it really becomes interesting when you look at it in the context even smaller of why we're here today, and that's AI, deep learning. Deep learning has just absolutely changed the field. And it's definitely one component that's well recognized. It's performance, all right? Deep learning just does an absolutely phenomenal job. You all saw that over the past several days at the middle conference, just again and again, phenomenal results, standards being broken, state-of-the-art being advanced by deep learning techniques. But I'm going to argue that the other component, the other reason why AI is succeeding and deep learning is succeeding is because it's fully embraced open source and open science. And we're going to see that in MONAI. That's the topic today. And so in terms of performance, what do I need? Again, you saw this all today, but here's a wonderful example of MONAI in use. And what we're looking at on the left is a video sequence. Granted, it's a simulated video sequence that we have. But on the right then is the real-time segmentation of the instruments, the needle, and the thread that's being used for this computer augmented or for the segmentation task that we see that's occurring live. And so this is, if you tried to write this using traditional segmentation techniques, distinguishing that needle from the grippers that are being segmented is very hard. Doing this in real time, very hard, but it's something that really we can all imagine coming up with a deep learning system that does this. And so the performance is there on so many levels. And then regarding the other component, the open science component, really, deep learning took off because of ImageNet, right? And that massive database that came out and the UNet and the networks that were built on top of that. And that was published via the Archive system. Archive is this wonderful resource for massive publications of computer vision, medical imaging, and so forth, and typically involving deep learning, but also other fields that is completely open access. And this has become such a powerful force that now you can submit to a conference and put the pre-conference paper on Archive. That's just accepted practice. Most publishers have had to fold and allow you to do that, IEEE and others. And then open access data. There's now wonderful resources for data out there. There's grandchallenges.org. I don't know, grand-challenges.org. That has amazing challenge data related to medical imaging. There's TCIA, which stands for the Cancer Imaging Archive out of NIH. If you conduct a clinical trial for a drug study or so forth that's funded by the NIH, they request that data goes into the TCIA. So there's studies in there, longitudinal studies, drug response studies, and so forth. And this is real clinical data. It's not data that was acquired for deep learning, all right? But it's real clinical data, so it's real problems. And so if you haven't tapped into that, highly recommend taking a look at that. Then there's common formats that are out there, and so much of this is now being released under Creative Commons by attribution license. And I recommend you all do that. That's really freely accessible data. Now, note that today's presentation, I'm actually in industry. I'll admit it, kitware, all right, but everything I do is open source. And we have NVIDIA here. They've been a huge supporter of MONAI, so grateful for their participation. But still, a lot of people, we occasionally bump up this. This is a little bit of, a sales pitch here or whatever, self-interest. A lot of people do start releasing their data under Creative Commons, no commercial NC, CC/NC license. I really don't recommend that. One, because we can't touch that. All right, it won't become part of MONAI because there's industry involved. Industry has been a wonderful contributor. NVIDIA's amazing contributor to MONAI. But also, I have yet to know anyone who made a dime off of selling data on the web. If you know any success stories of where someone has released something under a Creative Commons, no commercial license, and then a commercial company came to them offering them a lot of money, let me know. Been here doing this for 30 plus years, never heard that story. Anyway, moving on. The other, though, is software, and that's why we're here today, and that is PyTorch and MONAI, Apache 2.0 BSD license, really freely available. And that is the open science, which is driving deep learning. You can do all three legs of that stool of open science. They just dominate within the field. And MONAI practiced this from the start. So that first cartoon where you had 14 standards and then went to 15 standards, MONAI and George Cardoso and Perna Dogra, George from KCL, Perna from NVIDIA, they did a great job of realizing they didn't want that to happen. They didn't want to become the 15th standard that was out there. And so before, originally, there was in 2019, when they came up with this idea, and even earlier, there was DKFZ, all of these different groups had outstanding deep learning systems that they were using heavily within these different research labs, but they were completely incompatible with one another. All right, so you could come up with a UNet algorithm within one of those platforms and have a hard time converting that to work on another platform. And so the ability for these groups to collaborate, for the work to move forward, it was really a hindrance to it. But instead of coming up with a new standard, what George and Perna did is they contacted these groups and invited them to participate in the development of MONAI. So German Cancer Research Center, DKFZ, KCL, all of these other groups, they were actually part of the original development of MONAI. And so it really invited these other standards, these other experienced people to come together to define MONAI. And so open science is winning, all right? They also then limited the scope of MONAI to processing that core. We've expanded out from there, but it was focusing on that core. And they realized that coming up with a common software foundation is great, but we also really needed a vibrant community in order to support that, all right? This notion, if you build it, they will come, works for baseball fields and the movies and all, but it's doesn't really work with software. You have to be out there giving workshops like this, the project weeks and so forth. You have to be supporting it by promoting it, as well as supporting it online via discourse 24/7. And so really recommend you all get involved. And they've taken this to heart to come up with this vibrant community and build upon it. And in terms of the purposes of it, they realized that it was needed within the field. PyTorch was wonderful. They built on top of PyTorch as opposed to coming up with something completely different. But the way they built on top of it was a way that extended it for medical applications, because medical applications had specific requirements. Hansfield units for CT means that you probably don't want to intensity normalize the way you would do for other modalities. On and on of these different dealing with ultrasound and so forth, voxel spacing, network architecture. UNet was presented at MICI originally, is where it was introduced, and now everyone uses it. All of these things are medical specific, and they've been adopted by MONAI. And all of these things have been adopted in a way as a layer on top of PyTorch to make it even more reproducible. So we want to reduce re-implementations. We want to provide baseline implementation, demonstrate best practices. So really make this thing educational and something that you can build upon, and invite the best of the best out there to participate. So we really have open arms. There's over 150 people have now contributed to the development of MONAI. That's developers from around the world. It's people like you, guaranteed. And a key component of reproducibility, or a key contribution of reproducibility, is just going to be more and more paramount, I feel, as deep learning moves forward in the clinical domain. And that's because it'll be towards that ethical AI, identifying biases within the system, making certain it works on MR scanners from multiple vendors, from multiple operators at multiple institutes, and so forth. And so this reproducibility is just going to become critical within the medical field more and more over the next few years. And then what is MONAI doing? It's impacting the entire imaging workflow. And so going through these real fast, it's being used for image reconstruction. These people came up with an image reconstruction challenge, and they came up with a demonstration reconstruction algorithm using MONAI as part of this challenge. Group out of Stanford did that. Others are doing image segmentation, transformer networks, everything. Y'all have heard about that continuously the last 3 days. But beyond that, it's also longitudinal studies. There's now a push for registration capabilities within MONAI and multi-channel longitudinal understanding of the progression of data. And it's not data that's just images, but it's also now we're incorporating other clinical and lab results data, and it's not producing just segmentation of images as output, but it's doing survival prediction, outcome prediction, and so forth. And so it really is hitting every aspect of radiological imaging that you think of, but also now it's expanded quite a bit into pathology imaging. And you saw from that first video, we're doing endoscopy and video streaming that I'll talk about more. So hopefully you all have seen something that excites you and something that interests you in those slides that we had going forward, and it's touching on your area of interest. It's definitely touching on areas of interest for others beyond the field, because we've seen 1.1 million downloads for something that just did the 1.0 release September of last year, I believe it was. So essentially in the course of a year, we have 150 plus individual contributors, bunch of GitHub stars, derived projects on GitHub. So other projects on GitHub that have forked and make use of MONAI is just expanding rapidly. And if you do a Google Scholar search for MONAI, make that a required term, and then deep learning, you get 600 plus hits. And so number of publications, and after middle, that was another 600 publications, right? And so this number might have doubled. So it's really phenomenal what it's done. And as Michael was talking about, there's multiple components to MONAI. And there's the core, which we're going to talk about primarily today, the center part, which encompasses things such as federated learning, dealing with multimodality, supervised and unsupervised techniques, AutoSeg 3D, and then UNet and so forth. But then there's MONAI Label, which is the AI-assisted annotation, MONAI Deploy, which integrates your trained models into a clinical framework, and the Model Zoo that we're really emphasizing lately, which is a bunch of pre-trained models that you can use to kickstart your training of your own system, your labeling of your data, or deploy them within a clinical setting as a step in your processing pipeline. And so what is MONAI Core? It's actually a sequence or a hierarchy of methods that begin with low-level data I/O techniques, NumPy-based algorithms that build upon that, CUDA accelerated methods, transform network architecture, loss functions, and so forth. And then on top of that, we have the administrative components, the event handlers, loggers, and so forth. We then have predefined networks for GAN networks and autoencoders, UNet network architectures, dense nets, variety of different types of dense nets. All of these come down to, you can declare them with a single function call. So it's amazingly powerful at that level. And then we really are now looking at, with MONAI Label, MONAI Deploy, that end-to-end lifecycle capabilities of it. And with the 1.2 release, just to let you know how rapidly it's going, AutoSeg 3D was in the 1.0 release, I believe, and we did further enhancements of it with the 1.2 release. We now have NN UNet integration into MONAI Core, optimizing it for working with different groups. Metrics Reloaded, you're going to hear about that today. It's an amazing effort that exists both within MONAI Core, callable that way, plus as its separate repository. So its value is not just to MONAI, but maybe even some of your own work independent of MONAI, where you can look at this Metrics Reloaded and come up with clinically motivated metrics for assessing the quality of your segmentations, registrations, and so forth. So wonderful efforts that are building together that have even broader than MONAI impact. We're going to talk about bundling a little bit in here, and then lazy resampling is also this really cool way of accelerating the processing of your data by compounding your transforms, optimizing your transforms the way they're used in order to do your data augmentation or data pre-processing for your network. So we're thinking of all the different steps that we're improving on within MONAI Core. And so MONAI label, how many of you all had heard of MONAI label before? All right, about half of you all. And so that's great. We're making some progress. MONAI label is AI assisted annotation. And if you haven't, even if you're not interested in labeling your own data, you have access to already labeled data. I recommend taking a look at it. Our goal with this system is to reduce the number of segmentations of annotations that have to be done by an expert by 75%. And the way this works is we embed it within nice user-friendly interfaces. So 3D Slicer, how many of you all have, I'm on this roll now. How many of you all have heard of 3D Slicer? All right, good, 100%, we'll go with that. So 3D Slicer, it actually has a module that you can enable together with running a container on your system in order to run MONAI label within 3D Slicer. What'll happen then is it'll use an intelligent system AI-based system in order to select from your collection of data that you're making available to MONAI label via Slicer. It'll look and find out what is the data set that I need to annotate in order to most inform a deep learning system. All right, my base deep learning system that I've got. And it'll present that to you with its initial guess of your segmentation for your task. You then correct that segmentation and send it back to the MONAI label system. The MONAI label system will get that, retrain, get smarter, and then go ahead and say, all right, now given where I'm at in my segmentation results on my data, what is the next data set that needs to be annotated by the expert in order to best improve my performance? It presents that with an initial segmentation. You go ahead, edit that segmentation, you go from there. It's amazing how with just a few annotations, you really can train a neural network without ever writing code. All right, so this is just a really powerful system, and there's so much research that can continue to happen within this domain. A federated learning approach for MONAI label, would love to see that happen. People have dabbled in it. There's just so much that can be done, so many aspects that AI can really improve this difficult and challenging task. And so the way it works is it doesn't interface just with 3D Slicer, but you can also interface with OHIF. And if you have pathology images, there's DSA and QPath and other viewers that have now been integrated with MONAI label. And so you have these various clients that communicate with the server, which are available as containers that contain your AI algorithms, so your pre-trained models that you've downloaded or the models that you're trying to train. And then you have your collection of data, and all of this communication now has a nice Pythonic API in order to control and augment this communication process, as well as REST APIs and so forth. And so it's a wonderful way of getting data in the hands of clinicians, the experts in the field, for them to annotate it and build upon it from there. And why do you want to use this? Again, clinicians, it's a friendly way of doing it, but also for research scientists. Rapid way of prototyping. Am I going to be able to train an AI system on this new imaging modality that the physics department just developed? This is a quick and dirty way to get up and running fast on it. Trying different techniques for doing the learning. Doing research in active learning techniques, and then integrating your algorithm into 3D Slicer. MONAI label provides a basis for that. So now you've gone ahead and trained your system just by MONAI label, never had to write any code, or else you use the cool components of MONAI Core in order to write your own custom algorithm, train it up. So the next thing that you want to do, though, is deploy that, put that in the hands of clinicians for their routine clinical use. Well, MONAI is starting to address this, and Michael talked about this briefly, and that's via MONAI Deploy. All right, I didn't make this slide, so I would love to know where they got the statistics of 87% of data science projects never make it to production. I would say within the medical field, I'd hesitate, that's like 99%, right? I mean, if you look at all of the papers that occur within middle, there is this gap, this chasm that exists between the research that we do and our ability to deploy it within a clinical environment, all right? And so You're approaching a difficult problem. You're working with your clinicians. Your clinicians are giving you great data. You go ahead and you've got this wonderful rapport, and you've been working on it for 3 years under your R01, and now you go to deploy it in the clinic, and you realize you have to do DICOM communication. You have to come up with a clinically oriented visualization tool that doesn't show your images upside down. Clinicians hate that. And you know, that has the overlay of the segmentation results and so forth. You realize you have another 4 years of work of just administrative and housekeeping and everything like that to get your method out in the clinical field. Well, MONAI Deploy is meant to do this, because MONAI Deploy realizes that even though you've trained your neural network, there's all of this DICOM communication that has to happen. There's these pre-processing steps that have to happen, post-processing steps, visualization, and so forth. Well, MONAI Deploy is a presentation in and of itself. It's an amazing body of software that this group has developed, which allows you to offer your algorithm essentially as a service within a clinical DICOM-based workflow. So you can push images to it, get the results, get your DICOM structured RT struct or seg objects back in order to display them on traditional clinical visualization systems. So it's an amazingly powerful technique that's out there that saves you 4 years of work of moving your research idea into clinical practice. And what's powering all of this, the last thing is now what we want to do, now that you have your trained model, you've deployed it clinically, you want to make it available to the world. That's going to occur with MONAI Model Zoo. And that's really where we're focusing. I'll tell you in a second here on the 1.3 release. So the MONAI Model Zoo, this is our Hugging Face for medical images, all right? So this is, and hopefully you all know what I'm talking about when I say Hugging Face. What the Model Zoo is a collection of pre-trained models. And we want to make it really easy. What we're focusing on 1.3 is making it really easy so that once you've trained your model using Core or using Label, wouldn't it be great if you could just hit a button and it becomes publicly available, freely available to everyone via this Model Zoo? And Model Zoo right now makes it very easy to go to just monai.io, our main website, and there's a download button that's associated with each of these different systems, with each of these different pre-trained models that we have, and there's 24 plus of them at this point. And it allows you to download those models, and then run them, apply them, run inference using them on the data that you have. And these models are for CT segmentation, MR segmentation, BRATS, some of the best performing algorithms for BRATS, the brain tumor segmentation challenge that's been around for forever, the pathology segmentation, image registration techniques, and so forth. So really, if you're looking to get into deep learning, this is a great place to start. And as I said, what we want to do with 1.3 is make it even easier. We, again, want that button to appear within 3D Slicer so that once your experts has annotated your data, the model gets sent to the Model Zoo for other people to take advantage of. But we also want to make it so that you can take one of these models and tweak it for a different purpose using transfer learning, or use it as a backbone or as a foundational system, freeze the first set of weights, the feature layers, and then only train the back end for a new task. And so all of those capabilities, you can do them within MONAI, but they're difficult at this time, admittedly. We want to make it super easy, and that's the release that we hope to have out by September or October of this year. And so it's really powerful, coming full circle in its capabilities. And then last thing that we're focusing on, and this is, I need to kind of redo my definition of open source and open science, is this notion that hardware, because when you run these deep learning systems, you need to have it GPU accelerated, all right? You can definitely run all of MONAI on a CPU. I've done it and delivered it for customers. You don't have to have a GPU to do it, but if you have a GPU available, it's amazing how much faster it is, right? And what we're trying to do, though, is come up with a layer of abstraction for those hardware considerations so that the GPU acceleration is one component of it, but it's also interfacing with the robotic system. So ROS is a standard out there, the robotic operating system, open source way of interfacing with various medical and other commercial robots. Well, we're going to make MONAI via this HoloScan SDK compatible with ROS, so it can communicate with these robots. But also you have frame grabbers grabbing your ultrasound images. You've got ultrasound systems that are USB based, you know, the butterfly network and so forth. You want to be able to ingest that data. Clarius makes that easier. And so forth and so on. So all these devices out there, we're creating a library, and NVIDIA has been leading this charge. That's an open source, freely available library that's going to be part of the MONAI, Project MONAI platform. That's called Holoscan SDK, that allows you to interface with these systems really easy. And for clinical systems, that becomes more and more important as we go to augmented reality and virtual reality and so forth. And this is also then providing a pathway for delivering your system into a clinical environment, because you can run Holoscan SDK on a CPU. You can run it on any AGX platform GPU, but you can also run it on the Holoscan devices, these AGX and FDA approved version of the AGX devices that can run your accelerated algorithm from MONAI in a clinical setting, running MONAI deploy, communicating with these clinical systems, all as a shoebox that sits in a room somewhere in the hospital. And so this is really a complete bringing things full circle to deploying them within a clinical environment that I'm very excited about. And then the other next thing coming along, we need ideas from you all right? And so very much, again, community is a big part of MONAI. And so I've been doing all this talking, but I'm really happy to not talk typically. If I go a day without talking, I'm happy. But instead, I'm doing email, I'm checking out discourse, and I'm getting ideas and feedback from you all. And that's really the exciting part of working with MONAI, is it's getting stuff out there and seeing that impact, but even more so, it's getting back from you all. And we've had, some people have interfaced the documentation of MONAI with ChatGPT. Never saw that coming, right? So now you can have these conversations in order to understand the MONAI documentation. I mean, these ideas that come from the community are just phenomenal, and the community is you. So please get on this discourse in order to get your questions answered, and look at our Slack channel and so forth. Pop things in the issue tracker and on the discussion board to get your questions answered, but also give us feedback, give us your idea. And that's how MONAI gets better. It really is community supported. Apache would love to hear from you. And the Slack channel discourse and issue and discussion boards are just some of the ways of interfacing with us. We have a bunch of documentation out there, tutorials and so forth. Please take a look at them. And thank you very much for your time. Hopefully you will enjoy MONAI. Enjoy the stool that's now maybe with 4 legs with hardware involved of open science, and whether that open science is just within your lab or to the broader community, take advantage of it. It's a very powerful technique. Thank you.